Hello students, this is Honors Pre-Calculus Lecture 5A, Right Triangle Trigonometry, and the basic purpose of this lesson is to familiarize ourselves with the trigonometric ratios to figure out what that sine, cosine, tangent, what that stuff's all about, and then also start to think about how to start to figure out how to use those to figure out sides and whatnot. So the sides of a triangle. So just a little bit of a reminder, dealing with the special right triangles and something from geometry. If you've got two triangles and all the sides are congruent, so all the sides are the same, and all the angles are congruent, so you've got 6 pieces of information, everything's the same between two triangles, then we said that those triangles were congruent. Everything about one triangle is the same as the other triangle. However, if we had two triangles with all 3 angles are congruent, and we don't have any real information about the sides, then we could say that those were similar triangles. Right? One may be really small, one may be larger, sort of like a scaled up or down version of it. And we found out that the sides are proportional. That was sort of a geometry thing. So based on our activity, we found out that there's a 45, 45, 90 triangle, and there's actually a pattern that all 45, 45, 90 triangles, right triangles that is obviously, follow, and that is x, x, x root 2. So what that means is that maybe you have some sort of right triangle over here and you don't know what that hypotenuse is, but you do know one of the legs. You say, well, how am I going to figure that out? Well, I mean, one thing you could do is just do Pythagorean theorem. In this case, you're lucky because it's an isosceles right triangle that this side is also 6 over here. And you could do Pythagorean theorem, but why bother? We already did it generically with the generic 45, 45, 90 triangle. So we could just say, all right, this triangle over here, this particular one that we're looking at, is proportional to this one. So the classic formula triangle, so to speak. So we've got final answer is 6 root 2, as we'll see. You could just sort of like look at those and you might be able to figure it out off the top of your head and be like, oh, this is 6 and that's x, and according to this is x root 2, so this hypotenuse must be 6 root 2, and that'd be great thinking. That would be correct thinking. You also could, if set it up as a proportion, just sort of like a go-to way, you could say 6 over h, so this side over this side is equal to this side over this side, so the x over x root 2, and then go through the algebra, find out those x's cancel, multiply both sides by root 2, and divide both sides by multiply both sides by h. You get the h all by itself. Anyway, it turns out h is equal to 6 root 2 if you do your cross multiply process there. So that's an example of how you could solve a 45, 45, 90 triangle. If you've got a 30, 60, 90 triangle, you draw your triangle. Let's say you've got across from the 30, you've got a side 4, and we're looking for m and or n. Well, you could draw the 30, 60, 90 generic triangle over here. Across from the 30, it's x. Across from the 90, it's 2x. And across from the 60, you've got x root 3. And then just go to town. One thing, you just be like, all right, well, whatever's over here, we've got double it up here on the hypotenuse. So we could be like, boom, boom, right there. M must be 8. Or you could once again set up the proportion. You could say 4 over m is equal to x over 2x, and that's what we got set up here. If you carry that through, you'll also get that same idea that m is equal to 8. You might be able to just look at this real quick and say, okay, all right, over here we got x and then x times root 3, so this must be 4 times root 3. You'd be absolutely correct. Or you could set up the proportion 4 over n is equal to x over x root 3. And if you follow that process along, doing cross multiplication processes, then you get the same thing. Sort of the generic instructions are for solving a right triangle is we'll draw the special right triangle in the same orientation as the triangle that you're given. So notice up here I had my 45, 45, my right angle is in the bottom right. So I drew my 45, 45, 90 triangle, the generic version with those formulas there in the bottom right, so the right angle down there. On this 45, 45, 90 triangle, the right angle is on the top left, so I'm going to draw my 45, 45, 90 triangle with the right angle in the top left. That didn't come out very well. That should be an x. So we've got x, x, x root 2. And that will make it really easy if you want to do things. Now, in this case, our hypotenuse is 10, so that's kind of weird. And I've got that's equal to x root 2. All right, some of you might be able to be like, ooh, just divide by root 2. That's fine. That'd be correct. Going back to our proportion setup, you could say p, or 10 over p, this side over this side, is equal to this side over this side, since these two triangles are proportional. I probably should have put the angles in there. Anyway, so if you, in this case, those x's will cancel out, and you have 10 over p is root 2. Multiply both sides by p, divide both sides by root 2, and you end up with p is equal to 10 divided by root 2. And you can simplify that as well. This one just shows the same idea. Step number 1, I've got this right triangle, 30, 60, and I've got an 8, a D, and a C. So across, so I draw my right triangle, my special right triangle here in the same orientation. Notice I even, and this is great, I have that 30 side is definitely shorter than the 60. So anyway, I've got my x, 2x, and x root 3, and then whatever you want to solve for. Okay, so in this case, maybe I want to solve for c and d. I could say that 8 over c, this leg over that leg, is equal to x root 3 over x. Cross, those x's will cancel and then cross multiply. Find out that c is 8 divided by root 3. And in class, I'll probably then multiply this by root 3 over root 3 to rationalize the denominator. And then whatever number I get there, that's the cross from the 30 side, I'll double that to figure out what d is. And there's more examples in the homework. Then we moved on to SOHCAHTOA, which is sort of a sentence which is abbreviation for the sine, cosine, and tangent. And as mentioned in the activity, there are nicknames for the ratios of a given angle, or of the sides with respect to a given angle. Those ratios are the sine of a given acute angle is the opposite over hypotenuse. The cosine is the adjacent over hypotenuse, and the tangent of an angle is the opposite over adjacent. So for instance, if I were to look at angle y here, the sine of angle y is my theta, okay, would be the opposite, so 24 over hypotenuse, 25. The cosine of y would be the adjacent, so side 7, or the 7, divided by the hypotenuse, 25. And the tangent would be the opposite, which is 24 over the adjacent, 7. Okay? And I could do the same thing here with angle J or with angle L. I normally circle the angle and then draw a line across, so I can then label this as the opposite, this one's the adjacent, this one is the hypotenuse. However, it makes a difference if you're looking at angle L or angle J. I mean, the sine of angle L is the opposite from angle L, the opposite side, divided by hypotenuse. That's going to be 3 over 5. But if I was talking about the sine of angle J, then its opposite side is 4 over 5. And so the idea here is that the sine of angle L is not necessarily equal to the sine of angle J. Or as I put here, the sine of angle Y is not equal to the sine of angle X. I should have put maybe it's like not necessarily equal, because if you say, well, what if Y and X are the same measure, they're the same size? Well, then yes, they would be, because you're looking at that'd be a 45, 45, 90 triangle. For the most part, you're not. So the sine, cosine, and tangent depends on which angle you're looking at, because what it is the sine of that angle is the ratio of the opposite side over the hypotenuse. And you could have your triangle in different orientations, and I just kind of probably in class walk through. What if this is your angle, then the opposite is here and the adjacent is here? What if this is your triangle and you're looking at this angle, then the opposite would be this leg and your adjacent would be this leg. Opposite just means side across from it or opposite it, and the adjacent is the adjacent leg. Also, we only use sine, cosine, tangent at this time with acute angles, which means 0 degree or 90 degree doesn't make sense. So we'll find out later that we can expand these definitions, but for now, that doesn't. This would be nonsense to talk about the sine of a 0 degree angle, because you can't even make a triangle with a 0 degree angle, or You can't, if you have another angle in a right triangle, it's 90, then you'd have a 90 degree here and a 90 degree here, and those two sides would never meet in standard Euclidean geometry. Anyway, so then we can use the Pythagorean theorem and trigonometry to label some different things. So for instance, if we want to find the sine of this angle theta, hey, no big deal. Opposite, so 4/7, which right there, great, it's going to be 4/7, when whatever that decimal happens to be. However, if we want to find the cosine, we're out of luck, at least temporarily, because we're not given what this length is down here. So we would have to use Pythagorean theorem first to figure out what this side is, this adjacent side to that angle theta, and then let's say it was, oh, I don't know, 5.5. If this was 5.5, then the cosine would be 5.5/7. And then the tangent, so we already knew this right now, is 5.5. Tangent is opposite over adjacent, so 4/5.5. So sometimes you're going to have to use Pythagorean theorem first. And also, for the purposes of full disclosure, there are other trig ratios, 6 all together, sine, cosine, and tangent, which are those nicknames for those ratios. But then there's also cosecant, secant, and cotangent, and sometimes these are called the reciprocal identities because what they are is the reciprocal of sine. So it's 1/sine. Secant is 1/cosine. Cotangent is 1/tangent. So if you play that out, that's 1 over the opposite of hypotenuse, and if you have, something divided by a fraction, that's the same thing as taking that numerator, multiplying it by the reciprocal. So it turns out that it's just going to be the opposite over the hypotenuse over the opposite. Secant turns out to be the hypotenuse over adjacent, and cotangent is the adjacent over the opposite. If you compare those with these up here, you'll find out that they're just, like I said, the reciprocal. Sine, opposite over hypotenuse. Cosecant, hypotenuse over opposite. Cosine, adjacent over hypotenuse. Secant, hypotenuse over adjacent. They're just like I said, the reciprocal of one another. One thing students tend to do incorrectly is match the sine with the secant, because they're, the s's and the cosine with the cosecant. That's wrong. The way that you need to think about this is each one of these trig ratios there's a co that goes with it. So sine goes with cosecant, cosine goes with secant, and tangent goes with cotangent. So don't just let the s's don't line up those s's and the c's. It's the other way around. All right. So that's basically the quick summary. There is how to use special right triangles to solve problems, to solve sides on a right triangle. What sine, cosine, tangent are, namely the ratios of the acute angles. Sometimes using Pythagorean theorem and trig to find another side, and then also those other trig ratios. All right, thanks for watching.